In this video, I want to have a look at quadratic trig equations. So we're going to jump straight into an example. Our first one asks us to solve tan squared theta plus tan theta minus 2 equals 0 in the domain 0 to 360 degrees. Now we've solved problems similar to this in 2-unit called equations reducible to quadratics. So the way we solved those was we said let x equal something, so we're making a substitution. In this case, it's going to be tan theta. So if x is tan theta, then this equation is going to become x squared plus x minus 2 equals 0. Now we can go through and solve this for x first. So we'd factorize to x plus 2, x minus 1 equals 0, which would give us two solutions. We'd have either x equals minus 2 or we'd have x equals 1. Now we know that x is tan theta, so if we sub that back in, we'd have tan theta equals minus 2, or we'd have tan theta equals 1. And now we have two new trig equations that we need to solve. So if we do this one first, we can draw up our all stations to central diagram. We know that tan is negative in the second and fourth quadrants. Now 2 isn't one of our exact values that we know, so to find the related angle here, we're going to do tan inverse of 2. And that's going to tell us that our related angle is 63 degrees and 26 minutes. Now, if we take that in the second quadrant, so we'd have 180 minus 63 degrees and 20 minutes, we'd end up with theta equals 116 degrees and 34 minutes. Or in our fourth quadrant, we'd have 360 minus 63 degrees and 26 minutes to get down to this one. And that would give us 296 degrees and 34 minutes. So there are two solutions that make this true, but we also have to solve this one. Now, our all stations to central diagram, this time our tan is positive, so that's in the first or the third quadrants, and our 1 is one of our exact values, so we know that theta, or our related angle, is going to be 45 degrees. So theta is 45 degrees, or 180 plus 45, so 225 degrees. So we have four solutions for theta within our domain that make that quadratic equation true. Our second example asks us to solve cos squared x equals 2 cos x in the domain minus pi to pi. So the first thing I'm going to do is to bring all of that onto the left-hand side of the equation. So we're going to have cos squared x minus 2 cos x is equal to 0. Now I want to factorize that, and the first thing we look for is a common factor. So I'm going to pull cos x out as my common factor, and I'm going to be left with cos x minus 2 equals 0. So that means that either cos x is equal to 0 or cos x minus 2 is equal to 0, which would mean that cos x is equal to 2. Now to solve these, I'm going to draw a graph of cos x in the domain minus pi to pi. Okay, so pi here, minus pi down this end. Now we know that cos x starts at 1 and it'll drop down to minus 1 here, and if we kept going, it'd come back up to positive 1 at 2 pi, and it's going to pass through here at pi on 2. So it's going to come down and curve down to minus 1, and it's going to do the opposite in the other direction, and that's going to be at minus pi on 2 there. So our answer to this one, cos x is equal to 0, would be at minus pi on 2 or pi on 2. So x is equal to minus pi on 2 or pi on 2. Now to solve this one, cos x equals 2, well we know that cos x only goes between 1 and minus 1. So this section, this equation, has no solution. And that's because cos x is greater than or equal to minus 1 and less than or equal to 1 for all x. So it doesn't matter what x value is in there, our range is always between minus 1 and 1. So we have two solutions to that quadratic equation. All right, our last example asks us to solve 3 cos x minus 2 sine squared x equals 0 in the domain 0 to 2 pi. Now what looks a little bit confusing with this one at first is that we've got a cos and a sine. But we know from our Pythagorean identity that we can rewrite sine squared x in terms of cos squared x. So we're going to have 3 cos x minus 2 outside of 1 minus cos squared x is equal to 0. So using our Pythagorean identity to rewrite that. Now if I expand that out, I'm going to have 3 cos x minus 2 plus 2 cos squared x is equal to 0. And if I just rearrange that so that my squared terms first, I'm going to have 2 cos squared x plus 3 cos x minus 2 is equal to 0. Now to make this a little bit easier to see, I'm going to make that substitution. I'm going to let x equal cos x. Hang on, let's not use x. Let's use something else because there's already an x in there. Let's use, I don't know, a. So I'm going to have 2a squared plus 3a minus 2 is equal to 0. Now we've got a non-monic quadratic, so you need to factorize that. And if we factorize it, we're going to have 2a minus 1 a plus 2 is equal to 0, which means that we'd have 2a minus 1 equals 0, which is 2a equals 1, or a equals a half. Or we'd have a plus 2 equals 0, which means we would have a equals minus 2. Now if we substitute back in for those a's, we're going to have cos x equals a half, or cos x equals minus 2. Now this one's going to give us the same issue before, that it's not in our range, so there's no solutions for this one, but we can solve this one. So cos x equals a half between 0 and 2 pi, so we draw up our all stations to central. Cos is positive, so that's this quadrant or this one, and for a half our related angle is pi on 3. So that means that our x is going to be pi on 3, or this one would be 6 pi on 3, so that would come back to 5 pi on 3. So we've got two solutions in that domain which make this quadratic equation true.